Okay. Hello, everybody. So last class before spring break, woo. Spring break, woo. This couple of people asked, I don't have your stuff graded yet. Just been a personal problems have interfered with work. So I will have them graded and handed. All the things that we haven't gotten back, they will be handed back on Monday of after spring break. But solutions to those things will be posted sooner than that.
What page is that?
This is page 92.
Okay.
All those things will be, the solutions will be posted, and then later today or tomorrow there will be an exam review for exam 2 posted for the funsies. Yeah, so getting close to end of chapter 2. Last time we were talking about how to use implicit differentiation to our advantage. So implicit differentiation, as you remember, is just taking the derivative while treating y as a function of x, despite the fact that this stuff is all, where's all the verbiage? There we go. There we go. So as nasty as it can be sometimes, it's a matter of knowing that y is a function of x, so that if you have x times y, you have the product. And so you have to use the product rule and all that fun stuff. So all the rules we know and love can be used and combined, but one of the biggest uses of implicit differentiation is logarithmic differentiation. Now, the problems that we had here were not incredibly bad to do with logarithmic differentiation, but I do want to give an example later on in the notes. So, or like in the exercises. So look at 7F here. Look at 7F. That looks like it would be an absolute monstrosity, because you'd have to do a chain rule. And then you'd have to do, within that chain rule, then you'd have to do a quotient rule. And within that quotient rule, you'd have to do 2 product rules. And within those 2 product rules, you'd have to do a chain rule with each of them. It would be an absolute nightmare. But with logarithmic differentiation, we can split this up into 4 very, very, very nice logarithms that don't require much work at all. So this is a great example of using logarithmic differentiation. Then the other way that it becomes very, very important is the stuff that we were talking about last time. If you have a function raised to a function, so variables raised to variables, that's when you cannot use the power rule and you have to use logarithmic differentiation. There is no other way. Well, there is another way, but it's very, very, very convoluted. And if you want to know it, feel free to talk to me. I'm happy to show it to you, but it's just a matter of it's really, really tedious. And logarithmic differentiation does it very quickly. So for example, this one right here, it's another function raised to a function, because it's a variable, like it's variables raised to variables. So our only option, and yes, it does say f of x, but we can just rewrite that as y, because a function is just renaming y equals blah to f of x or g of x. So we're just going to make it y equals ln of x raised to the sine of x squared. And then what we're going to do, the reason why we do logarithmic differentiation, why we apply the logarithms, is because it allows us to bring that function down up front, that exponent out front. So we'll apply ln. And so then we get ln of y is equal to sine of x squared times natural log of x. Don't get it twisted. It's not natural log. It's not sine of x squared times natural log of x. Remember, that's natural log of the inside. We can actually, like, maybe it just so we're clear. So you're going to have ln of x raised to the sine of x squared. So the sine of x squared comes out front, and that's why we still have that ln of x. And that's okay. We can have a natural log of a natural log. Not unheard of. So Now we differentiate both sides with respect to x. Or you can write d dx if you want to, but derivative of natural log of y, that's implicit differentiation. Y is being thought of as a function of x. So it's going to be 1 over the inside, so 1 over y, times dy dx. Now this is going to require a product rule on the other side. And you can either do you can write your f primes and g primes on the side, or you can do it all in one step. If you want, if you feel comfortable doing it all in one step, be my guest. If anybody would like me to write the f primes and g primes on the side, I'm happy to do so. But I'm going to do it just based, just doing it all in one go. So this is our f, this is our g, and we're going to see we're going to need chain rules on those as well. So f prime is going to be cosine of x squared times 2x times, so that's our f prime, and then ln of x, plus g prime, which will be 1 over ln of x times 1 over x times sine of x squared. Which I'm gonna beautify in just a second here, make it look pretty, so that it doesn't take as much space up. But does anybody have any questions on the derivative on the right hand side? It's okay if you do. See, and I know I look really intimidating up here, but I'm not infallible, and I'm a pretty nice guy, I'd like to think. Yes, Kate.
So you wouldn't have to do the chain rule if like the sign was just X?
Yeah, if it was just sine of x, then you'd only have to do one chain rule. You have to do the chain rule on the ln of x. But if this was just, so Kate is asking, if this was just sine of x, then this wouldn't require a chain rule, only this would. All right. So last thing though is we want to solve for dy dx. We don't want it to just be 1 over y times dy dx. So what we're going to do is we're going to multiply both sides by y. To cancel the y on the left, and then we get dy dx, or preferably now f prime of x, because that's what the function is going to be y, which was ln of x to the sine of x squared, times, in brackets, 2x cosine of x squared ln of x, plus sine of x squared divided by x ln of x. And that is our derivative. So I just move the so I'm just jumbling things around to see how I feel, like to make it look pretty. So usually variables come out front, then exponentials, then trigonometric functions, then everything else. So that's why I've got it as 2x cosine of x squared, then ln of x. And then the other one, 1 over ln of x times 1 over x, that's just 1 over x ln x. And then the sine x squared, I'm just putting in the numerator.
Kind of like organize the best way.
Sure. So one thing that I could recommend, I would recommend, I didn't write it down when we were doing chain rule and stuff, but you can definitely do this. How would I like? Never mind. I'm rambling at that point. I don't remember what I was going to say.
Good morning.
Good morning. You can definitely like find these things off on the side. It's like label this as your F and this is your G, and find those off on the side. So F prime would be cosine. Oh.
On the very bottom to make it look pretty.
Like the rules. Okay, yeah, sure. Gotcha. Yeah, let's do like
Like there's no PEMDAS where
how you should make it look. And I want one.
Expressions. You know, to give them that, to put them, what do the people say? Un fuego, right? Is that
What?
like on fire? Isn't that what the kids say? Like to make it look cool?
Fuego means cold.
Fuego,
Fuego.
fuego. On fire. So like I don't know. That's what you kids say. I'm just trying to repeat what you guys are saying. Okay, to make it okay. I know because I remember seeing this when I came here. A student I asked my students like for good food recommendations, and a person said to go to I think it's Blueberry or it's a breakfast place that has blueberry French toast because they said that the blueberry French toast was lit AF. So to make your expressions. I don't know what the AF means. I'm kidding. I know what it means. I just can't say that to you kids. So to beautify your expressions, constants, variable, like x's, exponentials, trig, and then everything else. So constants come first, then x powers, then exponentials, then trig, then everything else. That's my typical convention. Everyone has their own little flavor on it. But later on, you get into mathematics. Some people even start to try and make their own notation, so there's no consistency anywhere. There's a field of mathematics called differential geometry, and because you're dealing with n-dimensional objects that have n derivatives. There's Einstein notation, and then there's superscript and subscript notation, and it's all awful. Both ones are stupid. But point being is this is a very, very good staple for how to make your expressions look pretty. So last little thing from implicit differentiation is vertical and horizontal tangent lines. So we know how to find a horizontal tangent line, right? You set the derivative equal to 0. Because if the derivative was 0, that would mean you have a slope of 0, which means you'd be a flat line. But how do you find vertical tangent lines? Typically speaking, vertical tangent lines will happen where the derivative does not exist. Sometimes it's not, but typically speaking, and you'll notice this with implicit differentiation, when you do a bunch of these problems, you typically get stuff over things or things over stuff. It doesn't matter, like you get a fraction. That's typically the answer. And so to find out where you have horizontal tangent lines, you set the stuff equal to 0. So stuff equal to 0 implies a horizontal tangent line. Whereas if you have things equal to 0, that will give you the vertical tangent lines. Now just in case there's a secret math UNLV teacher out there trying to say, aha, I feel I caught you. Like this works probably 9 times out of 10 or 99 times out of 100. If it ends up being that the fact that it makes it 0 over 0 instead of just like if it's an answer to both of them at the same time, that's when you have something weird going on and you need to look at it further. But for the most part, if you let the numerator equal 0, you're going to find horizontal tangent lines. If you make the denominator equal 0, that's where you're going to find vertical tangent lines. So find all the points, the coordinate points where the curve represented by the equation 9x squared plus y squared minus 18x plus 6y minus plus 9 equals 0. Does anybody remember what that is? What type of a curve is that? Math 127 stuff. It's an ellipse. So you would expect, since it's an ellipse, it's going to have 2 vertical tangent lines and 2 horizontal, right? Because it's going to look something like this or like that. So 2 horizontal and 2 vertical. So we should be able to find 4 values. So first off, if we're going to find the horizontal tangent lines, we need to find dy dx. So we're going to ddx both sides. I'm actually going to make this larger just because it's going to put in there. So ddx of 9x squared plus y squared minus 18x plus 6y plus 9 equals ddx of 0. And luckily for us, we're not going to, like, you're going to see that the numerator only has x's, denominator only has y's. So, and I promise, so like we're going to be only dealing with ones that are very, very nicely solvable. The solving other like multivariable equations, that's for 283 stuff. So all the problems that we have here, they should, like, if there was a problem on an exam or a quiz that had you do horizontal and vertical tangent lines of implicit differentiation, you should get nice things that are not too terribly hard to solve. So you get 18x plus 2y dy dx minus 18 plus 6 dy dx equals 0, because the derivative of 9 would be 0 and the derivative of 0 would be 0. So to find the derivative for an implicit differentiation problem, first you take the derivative of both sides, then you isolate the dy dx terms. So we get 2y plus 6 times dy dx equals 18 minus 18x. So that means the dy dx is equal to 18 minus 18x divided by 2y plus 6. Now, yes, we could simplify it. Yes.
Why is it? I guess it's the same. If it's 18 minus 18x, could it be negative 18?
Plus 8. Yeah, you could do negative 18x plus 18, however you want to do it. I just like to, if I can, I like to have my first term be positive. If I can avoid it, writing a negative sign, because then that's extra work, right? It should be like, it's either going to be, are you bringing this stuff over to the other side? Are you bringing the dy's, the dy dx's?
I keep forgetting that 18 is when you do that.
Yes. It's a good thing to remind us of. So if you decide to bring your dy dx's to the right-hand side, you might get a slightly different answer than what I get. And that's okay. That's fine. That happens. The main thing is that you're just going to be, your answer, if you were to factor out a minus sign from the top and from the bottom, you get the same answer because the minus signs would cancel. So it's okay if your answer looks like 18x minus 18 over negative 2y minus 6. That's the same thing. So for the horizontal, set the numerator equal to 0. So we have 18 minus 18x equals 0. That gives us x equals 1, right? But notice it asked for the points. It asked for the points, not for just the x value. Still need the y value. How would I find the y value? How would I find this magic y value? Plug it into where? The original equation. Let's think about y. There you go. Man, I'm hilarious. So why would we plug in 1 into the original equation? So remember what an equation is. It's the set of all the x, y values that satisfy that equation. That's the graph. The graph of this equation here is all the x comma y's that make this equation true. So if we found our x value, we plug in our y value, and that will give us the corresponding points on the graph that have an x value of 1. So plug into original equation. So we have so x is equal to 1, so it's 9 times 1 squared plus y squared minus 18 times 1 plus 6y plus 9 is equal to 0. Let's see here. You get 9 plus y squared minus 18. Oh, so the 18 and the 9 plus 9 cancels. And so we get y squared plus 6y is equal to 0, which gives us y equals 0 and, or let's factor. Let's do the whole thing. That gives you y equals 0 and -6. So our points are 1, 0 and 1, -6. So we found the y value. We got 2 y values for our x value. And that makes sense. That makes sense. Because as we said, there was going to be 2 points where we have a horizontal, 2 points where we have a vertical, 2 points where we have a horizontal. So, and it makes sense that they're stacked on top of each other. Because if you look at the graph of an ellipse, regardless of what shape it is, whether it's the like this shape or this shape, the horizontal tangent lines have the exact same x value, just 2 different y values. So it works out that way. That's good. So then for vertical, we're going to set the denominator equal to 0. So you have 2y plus 6 equaling 0. And that gives you that y is equal to -3. Yes, Paul.
What's that next to the 1 and -6, and that exponent, is that derivative?
Where?
The coordinates 1 and -6. What's down on the top right hand?
Oh, that's the page number.
Oh,
Page number. Valid point. All right. And so now plug in OG equation to find x. So we have 9x squared plus -3 squared minus 18x plus 6 times -3 plus 9 equals 0. And that would give us, so 9 positive 9 minus 18 plus 9. Let's cancel again, luckily for us, since we get 9x squared minus 18x equals 0, which gives us x equals, or we'll factor out the 9x. Let's go the full route, not cut corners. So you get x equals 0 and 2. So we have 0, -3 and 2, -3. The fun fact, you can actually find the center of the, given this information, you can graph these things to give you a sense of where the center of the ellipse is without having to do completing the square. In fact, I'm pretty sure you could figure out the equation now without having to do any of that completing the square nonsense. You guys remember doing that? So you'd have to, in order to find the center, you had to complete the square so you could get x minus h squared over a squared plus y minus k squared over b squared equals 1. Yes?
Yeah.
There we go. Don't even have like so you could do it now. Now you know exactly, like you can find the middle because you now know where the x value is of the middle and the y value is of the middle. It's a pretty nifty thing. Now you don't have to do that awful pre-calculus to find it. Any questions on that? Okay, so an executive decision made by me is that we are going to skip basically all of 2.6 except for the important stuff. So omit. This is not going, like this material here, page 1, not going to be covered. So if you want to see it, the inverse function theorem, suppose f is a one-to-one function such that f of a is equal to b. If f is differentiable at a, then f inverse would be differentiable at b. And furthermore, the derivative of the inverse function is 1 over f prime a. You do not need to know that. That is not really a useful theorem for anybody besides a math major. You're not really going to see that ever again until maybe your senior year of mathematics, if you decide to become a math major. The one variable, so this is the inverse function theorem for one variable. There's actually one for multiple variables. There's an inverse function theorem for multiple variables, and the proof is a monstrosity. I think I've told you guys about Rudin's book. It's a classic textbook that mathematicians use for real analysis, and Rudin was never one for adding fluff. His proofs, it's a great book, it's a horrible book at the same time. It is very, very bare bones. Like, the book is this big, but it's got the density of a dying star. It is very, 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 very dense. And when he made proofs of things, he only used as little space as possible. So like most of the proofs that take people like a page to write, he put into a paragraph, and it took him 3 pages to prove that. So it's an awful proof. This is very, very useful and fine. Like if you don't know how to find the inverse of a function, but you want to know its derivative, whatever that may be, not very useful for most people. So you don't need to know this. So we're going to omit this as well. The main thing I want us to know is the derivatives of inverse functions. So like everything before here, not on the exam. You can basically just take a huge marker and cross it all out. But these we do need to know. So let's box these bad boys in. The derivative of arc sine or sine inverse is 1 over the square root of 1 minus x squared. The derivative of cosine inverse or arc cosine is -1 over the square root of 1 minus x squared. The derivative of tangent inverse is 1 over 1 plus x squared. The derivative of cotangent inverse is -1 over 1 plus x squared. The derivative of secant inverse, let's see if I can remember without looking, it's 1 over the absolute value of x times the square root of x squared minus 1. Am I right? Yes. I can tell you, if you're going to need to use these ones, I will give these ones. You don't need to know these ones memorized. So don't need to memorize. If there is a problem on a quiz or an exam that involves it, I will tell you that derivative. The other 4 are fair game. But the trick to remember is just like before. The co-functions have the negative. Why? Good question. I haven't really given it much thought. Besides the fact that it is, I know. There's a field of mathematics that if you guys are planning to go into engineering and stuff, you're probably gonna have to take Math 285, which is differential equations. And a lot of the proofs in differential equations, is why I don't really like DiffEqs, is that most of the proofs of differential equations is because I found it, because that's what happens. And so that's one of the things. If you want me to show at some point, we don't have enough time to do it, but if you want to see a proof of why this works, the reason for it to work is actually the inverse function theorem. You can't find the derivative of sine inverse, cosine inverse, the formula for them, without knowing the inverse function theorem. So if memory serves, the reason why there's a minus sign has to do with the domain of the inverse functions. So when you're finding the when you're doing the proof, it ends up being like you have to worry about where your function is defined. So because of that, you have to tack on a negative sign for those ones. It just ends up being the case that because of where cosine, cotangent, and cosecant are defined, they're only from 0 to pi. You have to tack on that minus sign, if memory serves. But I'll look into that again and get back to you. Any questions? So we just have more derivatives at our disposal. So we can do a couple more problems. So find the derivative of the following: sine inverse of t squared. By the way, so just as so I have decided in these notes to use this notation for inverse function for inverse trig. But some books will use arc sine, arc cosine, arc tangent, arc cotangent. When it comes to exams, would you guys prefer arcs or inverse signs? So sorry, so arcs, yes. So for example, some people will write this as arc sine of t squared. It's too much writing. This is the argument, and this is the reason why some people will use arc sine instead. Because how do you define inverse sine to the -1? Because some students will see this and think this means sine of t squared to the -1, but it doesn't. So I can tell you if I'm going to make you have sine inverse to a power, I will make sure there's parentheses on the outside to do that. But how about this? Whenever it comes to one of these questions, if there is inverse trig on the exam, I will write sine squared and I'll put underneath it the version in arc cosine, or arc sine, so that you can choose whichever way you want to write it. I will accept either answer. That okay? So arcs. So the outer function is the sine inverse. So f prime of t. And you don't need to know these formulas, but it's yet, because we just learned them. But it's 1 over the square root of 1 minus x squared if it was sine inverse of x squared. So this is sine inverse of t squared. So it's going to be 1 over the square root of 1 minus t squared times 2t. Which means that f prime of t should equal 2t divided by the square root of 1 minus t to the 4th. Because of the chain rule, yes. This would be a good argument for why you should write arctangent in B, because now it's starting to look like you're seeing two tangents at the same time, so your mind can get a little bit clouded. So yes, thank you for letting me know that. I'm going to do that from now on, of writing it as both inverse and arc and the arc notation. So let's go through this. So this, we'll call this piece 1 and this piece 2. Let's find each of those derivatives separately and then bring them together with the subtraction in the middle. So for 1, that's a product rule, right? You can't see, is it too because of the damn light? I do anything here. Thanks. Better? Okay.
Much better. Thank you.
Yeah, of course. Thank you for letting me know. I thought I do that every time I come in here, and every time it goes back to being unfixed. Is someone messing with this and trying to actually let joy into the world? I don't appreciate it. So f prime would be 1. So it's going to be 1 tangent inverse of 2x. And then the derivative of tangent inverse is 1 over 1 plus your thing squared. So plus 1/1 plus 2x squared times the derivative of 2x, which would just be 2. And then times Rx. So to write it a little more succinctly, tangent inverse of 2x plus 2x over 1 plus 4x squared. A very, very common mistake, and I want to make sure that we're all clear on it. A lot of students will just write 1/1 plus x squared and then times the derivative of 2x for 2. But remember, it's you got to remember here that it is the derivative of tangent inverse of x. So in particular, the derivative, like ddx of tangent inverse of a blue box, or let's do green box, why not? I don't get to do a green box very often, would be 1/1 plus the green box squared times ddx of the green box. And that's going to be true for all of them. So just take whatever's on the inside of your tangent, put it into the squaring portion, and then times the derivative of that thing in the inside. Just so we're clear. It feels a little strange because we haven't seen something like that yet, but that's how it works. Is that okay? I just don't want anybody to get blindsided by that. We all cool? We all jive? That's what the kids say, right? They all jive.
We were talking about the 2010s. Now let me copy that.
Oh. I'm pretty sure people say jive still, right? Awesome possum, isn't that still a thing?
That's something.
No?
The chain rule, right?
Yeah, it's just a chain rule. It's just, this is a formal, sorry, can I get it quiet for a second? Leslie has a good question. So yes, this is just a chain rule in action, specifically for these inverse tangents, which kind of look a little bit different than what we're used to seeing. Because most of the time it was just like, okay, derivative of the inside, and it's just the normal formulation, but this one's a little bit weird. All right. So that was part one. Part two is not a inverse trig function. So this one is just going to be a chain rule. The derivative of tangent is secant squared. So this will be 1/4 secant squared of 1 plus 4x squared times the derivative of that, which would be 8x. Derivative of the inside. So that's going to be, just writing it pretty, 2x secant squared of 1 plus 4x squared. In terms of simplification, so I don't ask you to simplify, and I won't mark you down. But if you can, just as a kindness to me, if you can combine constants, please do so. So like if you have a 1/4 and an 8, simplify that to 2. If you have a 9 and a 1/8, please bring them together to be 9/8 out front as a constant, if you can. I understand that we're on a time crunch because we're taking an exam, so if you don't get to that, that's okay. But just, it makes it nicer on me. It looks prettier. So h prime of x then is going to be tangent inverse of 2x plus 2x over 1 plus 4x squared minus 2x secant squared of 1 plus 4x squared. This was the derivative of part 1. This was the derivative of part 2, and we were taking care of them by subtraction in the center. So, oh yeah, this one. Okay. Let's see here. What do I want to do? I'm going to skip this this next one and give it to you as I'll give you the answer. just so that you can have it for your notes. Feel free over the spring break, just bust this one out, you know. Like, if your mom wants you to do chores, have her do some of the chores with you by doing some of your calculus stuff, and she'll leave you alone. So dy dx is equal to 1 over the absolute value of x times the square root of x squared minus 1 times e to the x cubed plus 1 minus 3x squared e to the x cubed plus 1 secant inverse of x divided by e to the x cubed plus 1 squared. That is the answer, if you'd like to verify it on your own time. Mainly because it has a secant inverse. I can tell you with 100% certainty that in the 10, 15 years that I've been doing mathematics, teaching it and studying it, I think I can count on one hand the number of times I've been asked to find the derivative of secant inverse. Derivative of secant, yes. Derivative of secant inverse, derivative of cosecant inverse, I can count probably on one hand. So that's why I don't make you guys memorize it. As long as you know how to use the chain rule in that formula, I can give you the formula and I'd be happy with that. So, in the interest of time, since I want to get to related rates so that we get the bulk of it, I'm going to skip these ones. I'm going to skip these two ones here. And I'll post a video on how to do those ones. Just so that we have it, but I'd rather spend time on something that's a little like that's new. The main part of this part was to say, like, hey, we've got these new rules, so let's use them. I.e. finding tangent lines, finding implicit differentiation. So now you have every derivative rule on a cheat sheet. So feel free to use this cheat sheet. One of the things I'm always looking for, by the way, once again, with these notes, they are not infallible. They're not perfect. So I'm always looking for ways to improve them. If you think there's a better way I could organize this derivative cheat sheet so that you have something to study better, please let me know. I'm always interested in finding better ways to present the material. So, but this is all the derivative rules. Just as a reminder, you can probably I'm going to highlight the ones that you don't need to have memorized. You don't need to have this one memorized. This one too. These two do not need to be memorized. Really? Fine. And then this one and this one do not need to be memorized. All the other ones are fair game. All the other ones are fair game. Every other, a lot of them are I know it looks like a lot of rules, but a lot of them we've just been they've probably become second nature at this point. Just after how many times we do these derivative problems. They what? Then limits? And a lot of people would agree. I'm inclined to agree. I like derivatives a lot. Integration is my favorite thing. Not everybody's cup of tea, but I hope you guys enjoy it. Integration has far more reaching implications, and it's very, very cool. So those are all the derivative rules. Now we move on to everybody's favorites, related rates. So this is an actual application for calculus in real life. Now, the thing is, what you have to always give me a little bit of grace here, because of course, when you're rolling a snowball down a hill, it doesn't form a perfect sphere, right? But it forms close enough to a sphere, just like how the Earth is not perfectly round. It's not perfectly spherical, but it's close enough. It's close enough. Ooh, I actually had a professor at Columbus State, where I used to work in the math department, who said, I see some legitimacy to their claims. And I was like, why are you teaching here?
Get out. So,
What legitimacy?
All I can say on that front, if you meet anybody like that, Have you ever worked in an office situation? Have you ever worked in an office and had a secret? It's,
Yeah.
if it's a big enough secret, it's gonna come out. And everyone's going to know in an office scenario, and that's just like 100 people.
It's nice.
So, anyways. So, the motivation is if I roll this perfectly sized snowball down a hill, it starts gaining mass, right? It starts rolling and starts getting bigger. If you know how big the volume is increasing, the rate at which the radius is increasing is proportional, i.e. a related rate. So, we have two different things. The volume is increasing at a rate. The radius of that sphere is increasing at a rate, and they are related to each other by the equation V equals 4/3 pi r cubed. It is. It's very, very closely related. Speaking as a person who's never taken a physics course, I don't know if this is a question that you'd see in physics, but I'd buy it. I'd buy it.
It's a little.
So in practice, if we know some or all or a few of the rates, we can solve for one of the other rates. So like one of the classic examples that I like to think about is imagine an oil tanker has spilled into the ocean, which should never happen, but apparently does. That oil is being leaked out, like their systems have a way of gauging how much oil is in the tank, right? So they can figure out how much oil is being spread out. Like they can see how much volume of oil is being spilled out into the ocean. So you can use math to figure out how big that oil spill is going to be and how soon you need to stop it, ideally immediately, but like you can realistically figure out how much time is going to be needed to fix it. So this is an actual real life application. Now, but just like always, it's a model, not an actual precise element, because the ocean isn't going to make a perfect circle from the oil spill. It's going to ebb and flow, but you can get a good estimate by being careful. So the general approach to how to solve these ones. Now, some people do it differently. This is the way that my professor, Dr. Jennifer Taggart did it, one of my favorite professors at UW, and I loved her method so much that I stole it. So you want to read the problem carefully. Make sure you take the time to digest all the details, aka read the problem. I know it seems stupid. I know it seems stupid for that to be a step of this process, but you'd be surprised at how your mind works when you're under pressure. When you're on an exam, you want to read things, you want to answer things as fast as possible. Don't do that with related rates problems. Take time to read it. And then step one is draw a picture if possible. Draw a picture. You'd be surprised at how useful this can be. And my reasoning for that is it helps you visualize the shape. And once you've got the shape in mind, you can figure out the formulas. You can figure out a lot of different things. And then what I like to do, this is the most important step, is write down, ideally in 2 columns, what you know and what you want. So abbreviate that to know and to want if you want.
Exactly like physics.
Okay, they do this in physics. Awesome.
Everything we have to draw a picture and label everything, and then you make a table and you write everything on the table.
Yes.
No,
Physics is pretty fun though.
it is fun. You get to throw things, and that's my favorite.
So
part.
one thing I want to add under step 2 though is it doesn't have to be perfect. And sometimes you include information that's not needed. That's okay. Like it's just meant to be there. It could help. Why not write down? If it doesn't help, that's not a big deal. You didn't spend too much time writing down additional information here. But I'd rather have more information to work with than less and have to go back to the beginning and back to the drawing board and keep going backwards and forwards. So try and write everything that you know. And as it says in the note, you should have at least one formula that relates the objects in question. So like radius and height, or length and width, or angle and height, whatever it may be. So differentiate your formula or equation that you found with respect to your desired variable, typically t for time. But remember your differentiation rules and the chain rule, especially the chain rule and implicit differentiation. Implicit differentiation especially, because all of your variables are going to be considered as functions typically of time. So as time goes on, the radius increases. So the radius is a function of time. As the time goes on, the volume increases. So volume is a function of time. So you're going to differentiate the equation. You're going to differentiate both sides of it, and you're going to solve for your desired rate. This is where you should start plugging in your known rates and values. Don't plug them in before that, because if you plug in the value before that, it now becomes a constant, and you take the derivative of the constant, it becomes 0 when it isn't. Does that make sense? So don't plug them in before you differentiate. You'll end up losing a lot of information. And then reflect on not just the problem, but your life and why you're taking Math 181 in the first place. I'm kidding. Reflect to make sure that it makes sense. If your ball is increasing in size, but you find that your rate of volume is negative, that's an indication that you maybe did something wrong, right? If your ball is increasing, if the rate is increasing, the volume of the ball should be increasing as well. So if your rate is negative, that doesn't make any sense. If you're getting a number that's like incredibly small or incredibly large when it shouldn't be, that's an indication that you might want to check it and make sure that everything works. So here are some useful formulas for volumes. Sphere, 4/3 pi r squared. Cylinder, pi r squared h. Cone, pi over 3 r squared h. Box, length times width and height. Surface areas. Surface area of the sphere is 4 pi r squared. Cylinder, 2 pi r h plus 2 pi r squared. Cone, that's like the weirdest one. Pi r times r. So for these ones, you don't need to memorize these formulas. I will provide them. The only one, like, I won't provide. We all should know the Pythagorean theorem. We should all know the area of a sphere, a circle, and the circumference of a circle. You want to know a cool way to memorize it? The area. So check this out. Check this out. This is a very, very fun thing that I want you guys to just ponder about. If you took the derivative of the circle formula with respect to r, what would you get?
Say that one more time.
So if you were to take the derivative of this function, a equals pi r squared, if you took that with respect to r, what would you get?
2 pi r.
2 pi r. What's the circumference? 2 pi r. The sphere, 4/3 pi r cubed. What's the derivative of that with respect to r? 4 pi r squared. The surface area, the bottom one. So if you have a two-dimensional object, the one-dimensional concept is the derivative. That's actually true in general. If you have an n sphere, just spheres. Spheres are probably one of the most the nicest objects we have in the world. Have you ever wondered why a bubble bubbles are always formed in spheres? Why?
Actually,
Because they're pretty, but it has to do with the properties of a sphere. Spheres are the only, say what? They're the strongest, and that has to do with one reason. They are the only shape that has constant curvature. So anywhere on the sphere, it curves the same amount. No other shape does that. No other compact shape. So that's a reason why we like them. That's the reason why we like them. Bubble freeze. Oh yeah, super cool.
they're so cool. Oh, I love them.
Okay, I'm sorry, guys. Let's get back to it. Point being is that You don't need to worry about any of these formulas besides just the basic ones like areas of normal things. In fact, you know what? Screw it. I'll just give all those formulas. It's not a big deal. Knowing how to use it is far more important. Okay. So, all right, let's do our first related rates problem. Suppose a snowball is rolling down a hill and is and coming towards you. As the snowball rolls down the hill, the radius is increasing at a rate of 0.45 inches per second. Determine the rate of change of the volume of the snowball when its radius reaches 14 inches. All right. So we have done step 0. We have read the problem. We have read it carefully. Now we have to draw a picture. Step 1. So we have this little hill, and you're down here, and you see this little spherical ball coming towards you, and its radius is increasing. Right?
That's when you run away.
You gotta don't do the Prometheus thing. Don't just run in the same direction as the thing falling. You gotta run at a diagonal. So it's increasing. And the reason why I drew this is to remind myself of a certain thing. So, and actually I should probably make this 2-dimensional or 3-dimensional. So know versus want. That's going to be step 2. What do we know and what do we want? We know the rate of change of what? The radius. So we know dr dt. Let's call the radius r. So we know dr dt is equal to 0.45 inches per second. Do we know any formulas that involve volume and radius? Yeah, the one on the previous page, the volume of a sphere. V equals 4/3 pi r cubed. That's another thing we know. What do we want? Thank God you guys can read, unlike my other class.
Thanks.
We want dVdt, but not only that, we want the volume we want the rate at which the volume is increasing, but we want, yes, at 14 inches. So we're going to do dVdt bar r equals 14. It's not wrong to say just that you want to find dVdt, but the reason why I write that bar r equals 14 is to tell me that I need to wait until the very end to plug in the r equals 14. Is that clear? So we have everything we need to know. We have a formula. V equals 4/3 pi r cubed. So step 3 is going to be, you take that formula, V equals 4/3 pi r cubed. And by the way, a good thing to keep in mind, if you're going, the formula that you use should have both of the variables that you're involving with in it. So we want dVdt, our formula has V in it. We have dr dt, our formula has r. If it had more variables, we need to know more. So we're going to differentiate with respect to t. So if you differentiate, let's actually just write that down. That's right. So ddt of v equals ddt of the right-hand side, 4/3 pi r cubed. So the derivative of v with respect to t, so v is a function of time, and that's just v, so it should be dv dt. Now I'm going to claim that the next side, the right-hand side, is going to be 4 pi r squared dr dt. And that's because of implicit differentiation. R is being implicitly thought of as a function of time, because as time goes on, the radius will increase. It increases apparently at a constant rate. Every second, it'll increase by 0.45. That's not necessarily entirely accurate. Sometimes it'll increase by a different amount, but that's what's going on with this problem. So, and let's go ahead and add the reasoning there. So d dt of r of t cubed equals 3 r of t squared times r prime of t. That's what's going on. That's why it's so 4/3 times the 3. That's why I've only got 4 pi r squared dr of t. All right. We're going to finish this one up and then we're going to take a break. So we have differentiated it. Now we do the step 4. We have differentiated it. Now we can plug in our values. If we plugged in r equals 14 from the beginning, we'd have v equals a number. And when we differentiate, we just get 0. And that wouldn't be correct. Paul, yes.
What was the end of reason? Is that like after two?
Say that again.
What's after the 3 f t?
Oh, that's an r prime of t.
R prime t?
Yeah.
Okay, I thought that was a derivative of t.
Yeah. So now step 4. So r was equal to 14. That was one of the known values. It was when r is equal to 14 inches. So dv dt is the thing we're trying to solve for. When r is equal to 14, it's going to equal 4 pi times r squared. R is now 14. So 14 squared times dr dt, which was 0.45. And so if I plug that into my calculator, I get an answer of 1,108.35, roughly. But John Doe student gets marked off 1 point. Why? Units. 1,108 what? Elephants? Yeah, hilarious. It's the joke that never gets old. So what are the units? Does anybody know? Close, not inches squared. Inches cubed. But the good news is, if you're ever uncertain, it gives it to you in the problem statement. If you look at the values in general, this is 14 inches quantity squared. So that gives you an inches squared. These are just constants, so they don't give us any units. This was already given in inches per second. So we have inches squared times inches per second. That gives you that inches cubed per second.
If you were just to put the. Yeah, you write the units in as you do the equations.
Yes. Sorry, can I get it quiet for just a second? So Elizabeth and Julie,
Yeah.
Julie.
Yeah.
No, you don't want to go by Julie. Julie and Elizabeth are exactly right. You can write the units as you go along, and then that can just take care of that for you. Personally speaking, I've done this so much that I already know what all the dimensions should be, but it doesn't hurt to do it along the way. All right, any questions on that? All right, let's take an 8-minute break. Let's come back at 11 o'clock. People watching the video, go stretch. And we'll be back in a second. All right, so we're back into it. So, for people joining in, we did 2 crosswords. So, an 18-foot ladder is leaning against a building. The ladder starts to slip away from the wall at a rate of 0.75 feet per second. How fast is the ladder sliding down the building when the base of the ladder is 7 feet away from the wall? This is one of those ones, honestly, drawing a picture is very, very helpful to figure out what exactly is going on. Because trying to just randomly come up with the formulas and stuff is not going to be easy. Please draw a picture. I give partial credit for pictures if there's a related rates problem on an exam. As long as the picture looks good. No, I'm kidding. It doesn't need to look good. It just needs to be a picture. So we got this little building. Oh, wrong color. Got a little house. And we have our little ladder. And it's sliding down. And it's sliding away. So it's sliding down and it's sliding away. And what we do know is that let's label some things on this. What do we know? Not the height of the building, but the length of the ladder is 18 feet. So let's write that down, 18 feet.
We also know that the ground is too soft.
So yeah, it's slippery.
It's 7 feet away from the wall.
Exactly. Like when we're trying to measure it, it will be 7 feet. Yes. So we know that this will be 7. We don't know what this is yet, but we can find that by a certain theorem. And then what we do know is that it's sliding, like slipping away from the wall, right? So which one is going to be the rate that we know? Do we know this one or this one? 1 or 2?
2.
2. So we know that, let's call this, actually what we're going to do is we're going to erase the actual numbers here. We're going to erase the numbers because that's going to be useful for later on when we're actually computing it. Right now, we want them to be labeled as general concepts. So let's call this side X and this side Y. And the reason why I say that, yes, Elizabeth.
Isn't it Pythagorean theorem?
Yes, it's going to be, well, the Pythagorean theorem is going to be very, very helpful here. So let's label those things because the ladder is not going to change in height. We don't got one of those fancy ones that extends and you can make it bigger. It's just a standard 18-foot ladder. So what we know and what we want. So what do we know? We know that X equals 7 when we're trying to measure it. The ladder is 18 feet. We can write that down. So ladder 18 feet. And we know. I'm going to put that under under want. Want when X is equal to 7 feet. When it's 7 feet away, that we know we're going to want something. We don't know what yet. We want something when X is equal to 7. So. Yeah, what do we want? In terms, like in mathematically speaking, what do we want? Do we want like dv dt? Do we want what? Yeah. We want dy dt because we want to know the rate at which it's falling down. So we want dy dt when X is equal to 7. Okay. So that's all we want. That's the only thing we want really right here. Now, do we have any ways that we know how to relate X? Is there anything else we know before writing down the formula? The 0.75. What is that? The derivative of what variable? X. Yes, German was right. It's dx dt. We know that dx dt is 0.75 feet per second. Now, there's got to be a way to relate X and Y. And Elizabeth gave it away. Thanks a lot for spoiling the fun for me. No, I'm kidding. The Pythagorean theorem. We've got a right triangle. First thing that should pop into our heads would be either right triangle or area. We're not being asked to find an area or anything like that. So area wouldn't really make sense here. It might help. And so you could write A equals 1/2 base times height. It's probably not going to help, but who knows? But I would say X squared plus Y squared equals 18 squared. Or what's 180? What's 18 squared? I don't know that off the top of my head. I don't have my
324.
324. What happened to that? Oh, there it is. Wait, did I change this around? Yeah, I did. Oh, crazy. Okay. So x squared plus y squared equals, what was it?
324.
324. All right. So we have a way to relate x and y. So we know when we differentiate, like not we don't know this yet, but once we start working through these a lot more, we're like, okay, we're gonna have to differentiate this formula, which means we're gonna have dx's, dt's, and dy's, dt's. We have a dx dt, we want to solve for dy dt, so this formula should work out for us. This formula should be good. So we're going to differentiate with respect to t. So ddt of the left-hand side is going to equal ddt of the right-hand side. And so ddt of x squared plus y squared equals ddt of 324. And notice that this makes sense, by the way, that the right-hand side, the derivative of the hypotenuse is going to be 0 because there's no change in the hypotenuse. The ladder is staying fixed at 18, so it doesn't change its rate. Now, sometimes that might, like, depending on the context of the problem, maybe there's an added thing going on here. Maybe I say that as it's slipping out, it's one of those awesome ladders that can be extended, and then that rate happens as well. But this one, this is a fixed ladder, so the derivative of that should be 0. So we get 2x dx dt plus 2y dy dt equals 0.
That, 324.
Yeah, 324.
Okay.
Okay. So we've differentiated. Oh, Elizabeth, yes.
Why does it go to 0?
Because it's the derivative of a constant.
Got it.
Yep. That is a fixed. There's a fixed ladder, so it does not have a changing rate, so it doesn't increase or decrease in size. So we now can plug in our values. So, but I'm going to do a little thought bubble over here. X equals 7. What is y? Right? Because we're like, we know what dx dt is, it's 0.75. We know what x is at 7. We want to find dy dt, but we can't have another variable that we're trying to solve for. That would be like, then we're trying to solve a 2-variable equation, which we cannot do in this course. How can we find y? Solve for y in the Pythagorean theorem, right? The Pythagorean theorem would tell us if x is 7, our hypotenuse is 18, what is our y value? We can find it. So use Pythag. So 7 squared plus y squared is equal to 18 squared. Y squared will equal 18 squared, which was 324.
Yep.
So 324 minus 49 is 275. So y is equal to the square root of 275. Yes, there technically should be a plus or minus, but remember, we're dealing with an intrinsically positive idea of length, so we can't take the negative version. So we could use an we could use an approximation here if we want to. We don't have to, though. Since I'm grading this, and it's not like, since I'm grading these problems and I'm not WebAssign or MyLab or anything like that, you can round early if you want. I don't take offense to that. My recommendation whenever you're trying to round something is don't round until the very end. But if you are going to round before the very end, round to like 6 or 7 decimal places. Try and round to as many, like write as many decimals as you can for that number, because that's going to give you the most accurate answer. So I just fine. I will be okay either way. I'll be looking, if there's a problem on this on your exam, I will be looking for your work and making sure that based on your approximation or whatever, it's correct. So x is equal to 7, y is equal to the square root of 275. So we have 2 times 7 times dx dt, which was 0.75, plus 2 times the square root of 275, is equal to, or then times dy dt is equal to 0. That is to say that dy dt is equal to negative 2 times 7 times 0.75 divided by 2 times the square root of 275, which is approximately, so 7 times 0.075, divide that by square root of 275. You should get roughly, that doesn't seem right. Seems like too small of a number. Oh. There we go. I accidentally, okay, so roughly 0.31 or roughly 0.32, negative 0.32. And what should the units be? It should be the same units as x, feet per second, because it's measuring a distance. But I guarantee you, you'll get feet here, feet per second. This is in feet, so the feets cancel and you just have feet per second. So, any questions on that? Yes. And so here's the thing. Here's the thing we have to think about. So the reason why it makes sense that this answer is negative is if you look at our picture. Actually, I'm going to do it. I'm going to redo it again because I can do something really, really super cool. So.
Yeah, I like it.
So as this goes down, you see that the height gets smaller and smaller. So that means that it's decreasing in height, which means that its rate should be negative. So, and then this then becomes a good point of English language versus mathematical statements. So we would say that it is its rate is negative 0.32 feet per second, but we would say that it is decreasing at a rate of 0.32 feet per second, not negative 0.32 feet per second, because you can't be decreasing by a negative amount. Does that make sense? So that's just verbiage. I'm pretty chill with just boxing in the DRDT or DVDT or whatever it is and just calling it good. You don't need to write an English statement for me, but it's fine other way. Yes. Mm-hmm. So that's the thing. So this is, I'm glad CR brought this up, and I think I understood your question correctly. And if I didn't, let me know. So why wouldn't it just be 2x? And this is where things get a little bit hairy, because we're so used to seeing x as our variable that when we take the derivative, we think it'd be just 2x. But remember, we're taking the derivative with respect to t, because x and y are both being thought of implicitly as functions of time. So we're doing implicit differentiation on both of them. So both are functions of time. So when we take the derivative, it gets that 2x times the derivative of the inside, which is x prime. Does that make sense? That was your question, right? Yeah. Yeah, that's a very, very good point. So when you're using the variable x, remember that you're taking the derivative with respect to t. So it's like you're doing the derivative on y implicit differentiation for both variables. So you have to have that dx dt or that dy dt. So
maybe because like I think the notes are I really appreciate.
Okay.
So you knew that dx over dt was 0.75 and not dy over dt.
Yes. dy dt was. So it doesn't say that explicitly. It says it uses English. Yes. Yes. And that's another reason why to have the picture, because it allows you to decide what your variables are. And so this is a thing that I always talk to my when I was teaching Math 95. Math 95 required you to learn how to solve systems of equations, and then they did word problems with that. And if you define your variables at the beginning, then you don't need to write an English sentence at the end because everyone knows what the English sentence is. So like you've already said that X is this and Y is that. So you can just say dx dt is negative 0.35 and call it good. But if you don't label what X and Y are from the beginning, I have no idea what dx dt means. What variable is that? Like, so if you don't draw a picture and don't define what your variables are, there's no way to know. You know what I mean? Okay. Okay. This is everyone's favorite.
It's tank.
And we're not gonna have enough time. We have 3 minutes. So we're gonna call it good today. We'll call it good today right now. We'll pick up on Monday after spring break with this problem. And we'll go from there. You guys have a lovely break, much deserved. To quote my friend's mom when he was going on his trip to Europe when he was 16, make mistakes. It's the creepiest thing she'd said to him. So make mistakes. 'Cause you're on your fun time. So do the stupid things. Have a great break, guys. Yes. You can get rid of it. All right. I'm gonna see you guys later. Have a great break, everybody. See you then.